Everyone, Mr. Neighbor, and we're talking about forces with Newton's first and second laws. This slide is talking about the net force, which we've talked about already, but remember the net force, or sometimes called the resultant force, is the sum of every single force acting on a mass. So if the net force is zero, then there is zero acceleration present. But that doesn't mean that the object isn't moving. So we really want to hit that point home. So for example, if I'm holding an apple, I have a couple forces acting on me. I have the force due to gravity acting on me, pulling me down. Sorry, the apple pulling the apple down. And then I have a normal force, a surface force, holding the apple up. Okay. When I move my hand upward, I'm applying more normal force than gravitational force. The normal force will change. The gravitational force, that can't change. It's always going to be that because the Earth is only so massive. So when we add these two vector quantities together, this is the gravitational force. This is the normal force. You will see a distinction in their lengths. And this right here in red, that is the resultant force or the net force. The force that shows you this is accelerating. Then if I stop that motion, the normal force returns to being the same size as the gravitational force. There is no acceleration. And when I add those two forces together, they will be the same and you will have zero net force. So there is no net force. So when I can't draw an arrow, I write zero with an arrow over top of it, saying there is none. We use the word equilibrium sometimes. That's when all the forces are balanced and the object is not moving if it's in static equilibrium. If an object is in equilibrium but it is moving, we call that dynamic equilibrium. So if we go back and look at this apple, this is static equilibrium. This is dynamic equilibrium. Equilibrium because the arrows cancel each other out, just like over here, the arrows cancel each other out. But here, it's moving at a constant velocity. Actually, I think when I was drawing this, I said that the apple stopped, but the apple is still in motion. However, the normal force and gravitational force are now balanced. So that apple is still moving up, but it's at a constant velocity. So dynamic equilibrium, static equilibrium. So how does an object actually start moving? It starts moving by an acceleration by a net unbalanced force. After that, it doesn't need a force to stay moving. A lot of people think there always needs to be a force for an object to stay moving. It doesn't. If you are in outer space, if you push something, that something's going to go on forever at that velocity until it encounters another net unbalanced force. So that's very, very likely that's going to happen, whether it's another planet or asteroid or a moon or something else, but it's most likely going to encounter something if you push it in space. So to actually start a motion, you need to have a net unbalanced force. There cannot be equilibrium if you want to start a motion. We talked about a lot of different forces with tension, with applied. I want to talk about friction though, because friction is pretty important. There's different types of friction, but sliding friction is what we're concerned with a lot of times, and fluid friction. So how big sliding friction is depends on how rough the surfaces are and how hard they are pushed together. So this is a very, very rough surface. So that's going to be a lot of sliding friction. This is not a very rough surface, the surface and then the object. So that's going to be a little bit easier to push on. And sliding friction can be broken down into static and kinetic friction. It's harder to move an object when it's actually still because these ridges line up and they kind of form their own grooves. So it's hard to get them out of that groove. But as soon as you start moving them with kinetic friction, it's just those tips bouncing along other tips. So it's easier to move when it's in kinetic friction. Static friction, very, very hard to move. So the force due to static friction is always going to be more than the force due to kinetic friction. Okay. Okay. Retract that statement. The static friction maximum will always be more than the kinetic friction maximum. There's a lot of range to static friction, but the maximum is always higher than the kinetic, which only has one number. It doesn't have a range. Fluid friction, you might think of this as air resistance. It's when it moves through a liquid or a gas, a fluid. So air resistance is the most common type. You can think about when you also fall through water. That is a type of fluid friction too. So some practice. A little boy and his dad are pushing a box across the floor. The dad then stops pushing the box, and the box comes to a stop with only the little boy's force. How big is the force of friction in this situation? Draw a free body diagram with appropriate arrows shown. So here's my box. That boy at this moment is pushing the box all by himself. So this is the force of the boy applying to the box. The force of friction is also opposing this. Because the box is coming to a stop, that means the force of friction has to be bigger than the force applied. So the force of friction, which in this case would be kinetic friction, is bigger than the applied force due to the boy. Because of this, there is a net force, and that net force, when I add these two vectors together, the force applied, the force of friction, I have a net force in this direction. I have an acceleration in this direction, which means it's slowing down the object because the acceleration is opposite the motion. So maybe I should have clarified that. I want this to be the direction of motion. Okay. All right, here we have the same setup. A little boy is trying to push a box across the floor but can't. His dad helps him get started, and then the boy can push the box on his own and can move it at a constant speed. So let's look at it as the boy is moving it at a constant speed. So the boy is applying a force this way to move the box, and it's going at a constant speed. So that means there has to be some other force to cancel out this force applied, and that would be the force of kinetic friction. In this case, the boy is able to apply enough force to equally balance the kinetic force of friction to have dynamic equilibrium. Before, when the boy and the dad were helping each other push the box, this is the boy's applied force, this is the dad's applied force, and here's the friction force. Notice how big the applied force is here. So the box would be accelerating there. But as soon as the dad gets rid of his force, we have this force diagram, and we see that the net force is going to be to the right. So this little leftover bit right here is the net force in blue.